Well, good morning to all of you. Thank you for coming. My thanks too to Index Fresh for extending an invitation to come and talk to you. So why is it that I am so popular today? I know why. Because in the America's Cup, New Zealand was up 8-1. And New Zealand lost 9-8. So you're here to remind me that New Zealand lost the America's Cup. This morning's presentation is called Reading Your Trees. Reading Your Trees is a booklet provided to New Zealand growers which shows different expressions of the trees. It shows trees with heavy bearing, it shows trees light bearing, it shows trees with different shoot types. It shows trees with heavy spring shoot growth, no shoot growth, heavy summer, turn it off. Heavy summer shoot growth or no shoot growth, and so on. It shows different stages of root rot development on the trees. It's an interesting concept, reading your trees, because the tree itself came from the rainforests in Central America. In the rainforest, we had heavy litter. We had the tree always trying to get up into the light, into the canopy, a hole in the canopy. The trees were seldom did they bear fruit, and their flowering was also highly erratic. Now we take the same tree and we domesticate it. And so we create groves and groves of avocado trees, and we have to take the tree out of its natural habitat and bring it into this adapted habitat, whether it's in California, whether it's in South Africa, Australia, New Zealand, whether it's in Spain, whether it's in Mexico, whether it's in Chile, or whether it's in Peru. Okay. Domestication means that we need to understand how this tree actually works. So when I write to you and say that tree expression is a composite of physiological, environmental, and cultural influences, what I mean is that we have to understand how trees react to the things we do to them. How do they react when we water them, when we feed them, when we prune them, and so forth. All of these understandings allows growers to better read their trees. So today, my presentation is to endeavor to help you to better understand how to read your trees. The first is to ask, what are some of the factors behind what we see? You look at your grove, you see different expressions. What exactly are the cause of some of them? Well, some of it is carbohydrate availability, particularly in the spring, when you have all this tree activity. You have flowering, you have early fruit set, you have some root flush, you have shoot growth, all of this activity, and you late hanging some of your fruit. You need a high degree of carbohydrate availability in the form of starch. And when we don't have that, then we see an earlier senescence of overwintered leaves. And those leaves often the senescence is accelerated because of temperature, moisture stress, or nutrient deficiencies. And right now in California, you have a drought. And so there is a great deal of heat, not so much heat now, but certainly there is a great deal of moisture stress in the groves. And that moisture stress has certain effects on the way the tree will behave. And secondly, we have this issue of endogenous, or which another word for that is internal plant growth regulators, which are also known as hormones, and their influence on tree behavior. And we have 5 major hormones. We have gibberellins, we have cytokinins, we have auxin, we have abscisic acid, and we have ethylene. And they all work differently. Some are beneficial, some are much less beneficial. And they're all involved in each and every one of your trees in different degrees. So when you have heat stress or when you have drought stress, you have an increase in abscisic acid. When you have senescence of leaves, you have an increase in ethylene. When you have a root flush, there's a relationship between the flush. What triggers the flush? And we know that auxin triggers the flush. So besides what you see visually there is also going on inside your tree huge amount of activities, hormonally driven, which in turn provide the expression that you see when you walk your groves. And thirdly, there are cultural imperatives. We expect you to water them, to feed them. We expect you to keep them free of pests and diseases. And above all, we want your trees to have plenty of sunlight around the entire circumference of the tree. So, we raise a number of questions. We say to you, do your overwintered summer shoot leaves look like these? These are taken in Orange County, early March 2013, and you can see they're still here. They haven't fallen at all. They're still in good condition. I've been in this grove, by the way. They are in good condition. Yes, there's a little bit of tip burn over here and here, but the leaves themselves are still green. They are still functioning, which is important, because ultimately your avocado tree farms the light. The more light you have, the more it can produce starch and carbohydrate and carbon for its needs throughout the given year. So this is our picture, our first picture, and we can see that these leaves are still very healthy, photosynthesizing, and they're very active. The next slide shows overwinter leaves taken in Temecula. Now you can see that these look very different. There's a certain tiredness in the leaves. The leaves are droopy. There is, the color is certainly not deep green. It's a yellowy color. There is a little bit of tip burn somewhere along here. We sometimes see it. Here we can start see the beginning of the flower panicles, here, here, and here, and here. And we would say to you that if your grove looked like that, we would prefer that it looked better than that. That the leaves look still greener, the leaves are more functioning, because as soon as all these panicles come out, we're going to see acceleration of leaf drop. The third picture is one taken in San Luis Obispo. This one shows that here we are seeing accelerated levels of yellowing all over the tree. And this is only taken in late winter, and so these trees haven't yet come under pressure with flowering and fruit set and early shoot spring growth. But already you can see that these leaves here, and this will probably accelerate as time goes on. And if you go and take it in a simple context, does this leaf here, which is nice and deep green, does it photosynthesize as well as this leaf, which is yellow? Every time we allow our leaves to get yellow, their function diminishes. And if the whole idea of growing avocados is to create as much carbohydrate for, what am I doing here? It's as much carbohydrate for all the expression of the tree activities, then we want our leaves to remain as green as possible for as long as possible. So these leaves are likely to become yellower as time goes on, and these leaves then contribute to the tree far less than those that we remain green. And finally, we have one from New Zealand. And I wouldn't like to see a tree in New Zealand look like this, because here again, prior to flowering, and you can see that the whole tree is almost yellow in color. The flowers are just about to come out. And this is the sort of condition that we don't want, because in New Zealand, it is more difficult for us to gather the sorts of starch needs we require, because starch accumulates in the winter, and our winters are wet, they are cool, there is less sunlight because there's a lot of rain. And so it's harder for us. So trees like this are not in good condition, and we would be much preferred if we have green trees. And we know now from work that we have done in New Zealand that where we keep our trees deep green as throughout the winter and into the spring, they are producing much better crops than trees that are allowed to yellow like this. And this yellowing will only accelerate as the season progresses into the spring. So, let's begin with some principles. Now, I want you to get these principles clearly understood. First, when tree demands in the spring the flowering, the fruit set, the early fruit growth, the shoot development, and the late hanging of mature fruit on your trees exceeds the current carbohydrate supply in spring, then remobilization of starch from reserves is needed to satisfy the shortfall. In other words, all that activity cannot be supported simply by photosynthesis from current leaf growth. And so what the tree does then is the tree mobilizes starch from reserves in the tree, and it uses that to satisfy the shortfall. Okay. That's in spring. But conversely, when carbohydrate production exceeds requirement, so now we're coming in autumn and winter, and we only have some fruit growth, we have a little bit of flower bud development, and we have a root flush during autumn and winter, then the reverse occurs. There is an accumulation of surplus carbohydrate which is mobilized as starch into the reserves. So your trees, every single tree that you have, loses or requires starch from reserves in the spring, and in the winter and in the autumn, when trees are more quiescent, in other words, there's less activity in the tree, then there's the ability of the tree to produce more starch than it needs for its current activities, and that extra starch goes into reserves. And the reserves, in turn, are then mobilized in the spring. So what you have, to give you an idea, at the end of winter, you have the highest concentration of starch, and that is used and diminishes until you come to a point probably around, let me just look at your time, around June or July, somewhere around there. And then as the tree, or it may be even later in California, and then as the tree, it goes into a quieter phase, the starch accumulation occurs. So we have this ebb and flow in your trees. Every year it goes on. The better your trees are in the sunlight, the better the condition of your leaves, the more starch you can create in each tree. The poorer your trees are in terms of shading, and in the case of the leaf quality, then you're going to produce less starch. So, having agreed on those principles, the next question is, any cultural practice promoting the maximum rate of carbon assimilation by functioning leaves, so we need our leaves to remain healthy, over autumn and winter will be beneficial for optimum tree activity in the following spring. Correct. What we're saying to you is that the expression and the performance of your tree in spring depends on how well you've prepared the tree for the spring activity. If the tree is well prepared, the tree flourishes. If the tree is poorly prepared, the tree suffers. So the better that you create the conditions for your trees, the better you're going to get in terms of outcomes. And finally, we say to you that a deficiency of mineral nutrients directly involved in chlorophyll synthesis, that's the synthesis to create the starch through photosynthesis. And the two elements that are important are nitrogen and magnesium. And if you look at the chlorophyll atom, you'll see that results in the formation of chloroplasts. What are chloroplasts? Chloroplasts are in the leaves, and they're the ones that accept the light, the sun's, the radiation, and they convert that into an energy and later on into form of carbohydrate. And that carbohydrate is then stored in the form of starch. So, if we have healthy leaves and they're well supplied with nitrogen and magnesium, they will do better. And that, as a consequence, results if they are short. If we are not, if we have a deficiency here and our leaves are yellower, then we result in the formation of chloroplasts with low photosynthetic efficiency and function. So it's all about your leaves. Healthy leaves produce healthy trees. Yellow leaves don't produce healthy trees. They don't produce healthy trees because they are under stress. They put the tree under unnecessary stress because the tree could do so much better if the leaves were green. So, this comes from a thesis for a Master of Science degree at the University of California, And the 2 points that were made, I've taken it from it. This was published in the California Avocado Yearbook some time ago, I think late 90s, I think. And he says, high yields are generally associated with a high accumulation of starch during the previous winter, yielding high starch levels in spring at the onset of flowering. Correct. So when you see now, you go into some of the groves, I haven't been groves in this region, but we've been to groves in Ventura and north of Ventura, and some of the trees are yellow. Now, what is the point of having yellow trees when it's a time when you can accumulate starch to prepare your trees for spring? And secondly, he says in his thesis, insufficient supply can lead to poor fruit set, reduced early fruit growth, and fruit drop. True. If you get poor fruit sets, if you get fruit drop, you have to ask yourself, why? Why did you suffer these consequences? And much of it is because the tree wasn't prepared and the tree did not have sufficient resource. And that resource is in the form of starch. And finally, there is a question, does flower starch content influence fruit set? And we have some work that came out of Spain, and we're going to share it with you today. So, this is a piece of work that it's done. The authors are Lou, the authors are Ruben Hofste, and Mary Appiah. It was done, I think, in 1999, and it was done at the South Coast Research Station. The trees were healthy, they were well watered, they were well fed, and they were looking at the activities of the trees, particularly leaf fall and new leaf growth in the spring. And these are some of the conclusions that they reached. They said, 40% of abscission of overwintered leaves by peak fruit set. So by the time we got to peak fruit set, 40% of the overwintered leaves were on the ground. Secondly, they said that by 17th of June, the remaining overwintered leaves represented a 90% decrease in carbon production. In other words, what he's saying then is that any of the leaves that were left on the tree, well, they didn't make much of a contribution to the overall carbon economy of the tree. They also said that the new leaf growth, maximum canopy carbon dioxide assimilation by new leaves, was attained in mid-June. So leaves started falling already in March, late March, early April. And we could only recover and get a fully functioning tree by mid-June. And we're going to show you the actual graphs. And finally, they said, well, when you have competition for carbon by fruits and by shoots, it often leads to poor fruit retention. And they found that as well. Because the more competition you have, the avocado tree has vegetative bias. So shoot growth is very competitive when it coincides with fruit set and early fruit growth. So we see it here. Here is leaf abscission. These are the old leaves, and you see how they're falling. We started here at the beginning of April. We ended here in June. And you can see how they're falling down, falling down, falling down. And over here, you've lost almost half your leaves. And at that point in time, you are here at net fruit set, you are at the peak fruit set, and half your leaves are missing. See? And after that, the leaves carry on. And now we have, and here we have leaf growth, and you can see how leaf growth grows, and it takes a long time before leaves are fully formed and fully functional. Let me explain that to you. We have a shoot. In this particular study, they found that the average shoot was 10 leaves. The emergence of the first leaf to the emergence of the last leaf was a time frame of 25 days. We also know that when a leaf emerges out of a shoot, it takes about 17 days before it can cope with itself. In other words, for 17 days, it has to import carbon in order to grow. After 17 days, it can export a little bit of surplus carbon to other leaves within the shoot. So you have 17 days, you have the 25, so 25 days it took to, for the last leaf to emerge, and that leaf again required carbon from other sources for another 17 days. And we can see here, and it's shown here where he's got net photosynthesis, you can see here that there's nothing, because although these new leaves emerged, they were all net importers of carbon from somewhere else. They weren't exporters, and slowly they continued like this. And to get a leaf to be fully functional in terms of photosynthetic activity, you need around 50 days. And for the whole tree to be fully functional, that took around 65 days. And you can also see here that as this competition continued here with leaf growth, okay, you can see that the competition here versus the competition here, you can see how less and less of the fruit set was retained, and by June there was only 1 out of 5 which remained. So it's a stressful period. The message to come out of that is that it is a stressful period for the plant because there is so much activity. And the key to remove the stress as far as practicable is to A, keep the leaves green and functioning, and keep them large if you can, and secondly, to keep them functioning, and to keep them on the tree for as long as possible into the spring. If leaves senesce and fall off early in the spring, then it means that your trees are not as well prepared as those trees where the leaves fall off later. Because what it's telling you is that early fall means you've got less starch in the tree. And later fall means your trees are better prepared and you've probably got more starch in the tree. So the next question you have to ask yourself is whether it is possible to improve leaf function over winter and delay leaf senescence. In other words, is there a way in which we can keep those leaves on longer? And we recognize that in Southern California, you have some issues. We're going to address them. You have salinity, you have heat stress, you have water stress. Yes. And some of that is unavoidable. Yes. And so we're going to tell you what the consequence of that is, because we recognize that in some cases you're not poor growers. It's simply that the environment in certain seasons is very harsh in terms of achieving the outcomes that you're looking for. So, we say the presence of a good carbohydrate status in the tree favors a desirable hormonal balance. True. Okay. Hormones are funny things. When the tree is under stress, the bad ones come out to play and they dominate the good ones. When the trees are in good condition, the good ones come out and they dominate the bad ones. That's a simple analogy, but it's true. When you have stress, you bring out the hormones that you don't really want. When you have healthy trees, you accentuate the good hormones that you do want. And we know what all these hormones do. We understand that. Okay. We don't understand it as well as someone like Carol Lovett, but we do understand it in a basic sense. So we say that when we have a lot of cytokinin, which is a growth hormone, it will delay leaf senescence. That's correct. So when you have a delay in leaf senescence, it's telling you that your trees are in better condition because you have one of the good hormones. While, in the reverse, abscisic acid, ABA, accelerates senescence. When your leaves are falling earlier than you had hoped, it's telling you that you've got a bit of the bad hormone rather than lots of the good one. So there's two ways to read the tree. You can say, yes, I went into the grove and the leaves all fell off. But there's another side to that. Leaves don't just fall off. Something triggers the leaves to senesce and prematurely and fall off. And some of that is involved in hormone. And thirdly, we say, senescence commences with rapid deterioration of the chloroplasts, therefore reducing starch synthesis. As the leaves yellow, they function less. So the overall production of carbon in your trees is reduced. So, as far as practicable, your trees should never, if they don't need to be, they should never be yellow. The only time those leaves should be a little yellow is when they have finished their entire lifespan and they are ready to fall on the ground. The next thing we notice is that a lack of function promotes aging. Let me explain that. You go into your grove. You go to the north side of your tree. Take a leaf, pull one off. Go to the south side of your tree, pull one off there. Feel the leaf on the north face, the shady face. It's thinner. Feel it. Go to the south face, where they're functioning, it's thicker. Yep. You didn't know that. Look, he's looking at me. He can't believe that. He says, no. That's a New Zealand story. No. You go this afternoon, go to the south face, they're thicker. Go to the north face, they're thinner. And growers have already done this when I told them this in an earlier meeting. But the lack of function, when leaves are not fully functional, they age prematurely. Okay. That's the first thing. Secondly, we know that mineral nutrition over winter maintains leaf color, longevity, and photosynthetic activity. And we've put New Zealand in there because we have a harsh winter. We have a lack of sunlight, we have cold conditions, we have a lot of cloud, we have a lot of rain and leaching and so forth. So what we're saying here is that although this is how we approach it in New Zealand, it is necessary for you growers, whichever way you want to do it, to maintain healthy green leaves throughout the winter. And that's the time now, so we can accumulate as much starch in your trees as possible. And often senescence is initiated by specific environmental and development cues. True, high temperature stress is one form where we get aging of leaves prematurely. Salinity is another. Moisture deficit is a third. And we're going to raise these issues with you as the presentation goes on. And finally, we thought about a thing called plasticity of group A cultivar. There are some who say that the average leaf span of a leaf is maybe 10 or 12 months. But we know that in New Zealand we can take a leaf which is produced in November and it goes the whole year to the next November and goes on till the next May. And we'll show you this. And it's important that these leaves remain on the tree because these leaves have certain specific functions which are helpful to the crop. Let me show you. Here, see, here is 17 months after. This is a determinate shoot. You had a panicle here, you never had an indeterminate, in other words, a shoot from the terminal bud, but you have a series of fruit, and here are still the leaves that supported the panicle when the panicle first emerged. And we know from some work that is done in the USA and Florida that these leaves directly behind the panicle are very important in supplying the panicle with starch or carbohydrate for the development of the panicles. So we don't want, as soon as the panicle comes out here, we don't want all these leaves to fall off. That is not a good sign. A good sign is when we have the panicle and we have the development and the fruit set here and the leaves remain on the tree. Those which we call proximal, which means they're just behind the panicle itself. See? So if you really want to drive your trees and drive health, you can have, so here we have newer leaves, here, see, here. But these are the old leaves and they're still functioning here. They're old now and they won't last more than a month or two, but we can. That's called plasticity. The harsher the conditions, well, true, the shorter the lifespan. But in New Zealand, which is quite mesic, which means that it's quite gentle climate, we can extend it and we can get leaf age much longer than other places in the world. So let's start with heat stress. When I was here, I was in John Cornell's orchard. It was May, about the 15th this year, and you had a heat wave, see? And I'm perspiring. I'm suffering. I'm not used to it. I'm looking for someone to sue. America's litigious. I just can't find anyone. You know, maybe the Environmental Society, maybe the EPA, maybe they'll take I can take a case. But anyway, it's hot. What happens? Let's tell you. If you can't, and often when it's a heat wave, and I accept this, that you may not be able to get enough water into your trees, regardless how much you irrigate them. I understand this. Okay. But we say low water availability reduces the evaporative cooling of leaves. What does water principally do? Water keeps the trees cool. It's a very important part of why water is required in the tree, is to keep it cool. Another purpose of water is because it extends cells. You have cells in the fruit, and if you want to fully extend each cell to get the biggest fruit, you use water, because water extends the cells. So you can have 2 fruit with the same amount of cell number. And if you have adequate water, unlimited, you'll get a bigger fruit, technically speaking. And if you don't, you'll get a smaller one. So the first thing is evaporative cooling. So the water comes into the tree, and then it goes out through the stomates. There's what we call transpiration, and there's a boundary layer, and that boundary layer is kept cool. Secondly, we do know this, that the leaf temperature of your leaves is higher than the ambient air temperature. We have some work of that in other crops, and it can be as high as 5 degrees Fahrenheit. Yep. So, you can always remember that if it's 40 degrees, the leaf temperature is probably a little bit higher. Thirdly, because leaves shut down as a consequence of very high heat stress, we get less photosynthesis, but we get more respiration. Respiration is the cost of all the activities within the tree. So we get a change in balance, in this case an imbalance, between photosynthesis, the activity in the tree shut down, but nevertheless, all the energy, there are energy costs. Even to take water from the roots to the tree is an energy cost. That energy cost is in the form of respiration. And so if you get a real severe case, you'll have an effect on leaf membrane stability, and you might get desiccation of your leaves. And we're already seeing in some orchards where leaves are cupping, or leaves are trying to turn. They are trying to get away from the sun because they are trying to maintain the relationships within the leaves as best they can. And we're seeing this. We actually saw this a couple of days ago on an orchard. And finally over here you can see the result. Carbon dioxide assimilation declines by 80% when the air temperature is 38 degrees in Hess. So your trees naturally shut down in order to protect themselves when you have a heat wave. But that shutdown comes at a cost. Remember that. Every time this happens, there's a cost. And that's unfortunate, but as you grow in warmer and warmer, hotter and hotter regions, these things have to be considered. This is a picture taken in New Zealand where we talk about photoinhibition and oxidation, and here you have the panicle just coming out and the leaves are yellow. Sometimes growers don't quite follow this. We're in winter, your winter. It's a beautiful day. The sun is shining, there's not a cloud. You should be out surfing the waves, but you can't because you're too old. You've got a hip joint replacement, some of you. Knee replacement, you over there, maybe. Who knows? See, so you can't go out, but it's a beautiful day. But it's only 10 or 11 degrees Celsius, the temperature. So I have all this light falling on the leaf, but the leaf can't cope with all the light because the leaf's function is lower because the temperature is lower. So we have ideal temperatures of around 17 to 22, 23 degrees. I'm not exactly sure centigrade. But when we get cooler, the consequence of that is that plants photosynthesize at a lower level. But we have, in this particular case, an excess of light, but we have the wrong temperature. And the consequence of that is that we have photoinhibition. Photooxidation is when we have a breakdown of chlorophyll. And so in New Zealand, we sometimes get these sort of conditions, And the way in which we try and correct them as best we can is through overwinter fertilization, or also we have seen that we can make some recovery if we spray them with urea and magnesium, but we don't like them to get as yellow as that before we intervene. And here you can see the reverse. Here's another orchard taken, and here the leaves have been kept. These are overwintered leaves, and these leaves are in very healthy condition over here, and here are the panicles starting to emerge, and this is a very different picture. So if I go back, would I like to see my trees look like that when they come to flowering in the spring, or would I like my trees to look like that when they're coming in spring? Am I likely to get a better fruit set when my leaves are in this condition coming into spring, or am I likely to get a better outcome fruit set if my leaves are looking like this in the spring? Good question. Very good question to ask. Salinity. We know that there is a rootstock sensitivity. Mexican is least sensitive, West Indian is more sensitive. Okay. We understand that. We don't have salinity issues in New Zealand. We have so much rain, we'd like to sell you some, but we're not sure whether your dollar, being what it is, whether you can actually pay for it. And there's also the question of whether we really want them. We'd prefer Chinese money at the moment. It's appreciating. Your money is depreciating. Did you know that? Yep. Just I thought I'd tell you. Anyway, next.
Mexican low sensitivity.
Am I wrong?
Yeah, you're backwards.
Oh, 10.
Maybe you got the dollar wrong too.
Oh, I like that. I like that. Now, I'm sorry. Thank you, Ruben. Huh? What is that?
Do you know how to sail?
No, it's in the literature. It's in the literature. What they've done is they've taken the different rootstocks, subjected them to different levels of salt, and then they've looked at the responses as a consequence. Okay. Next, salt exclusion versus salt inclusion. Plants have a difficulty. So you have the plants and the roots are bathed in a solution which is high salts. What do plants do? Plants have two choices. They can exclude the salts, but to exclude the salts means you have to exclude the water because the two are interlinked. So when you exclude the salts and you exclude the water, then you suffer from drought stress. So that's not really an option. In reverse, we can have salt exclusion, which means that the plant is ready and has to, and it accepts both the salt and the water. And that's what happens in avocados. Okay. And the consequence of that is that salt is sodium chloride, and chloride accumulates in the leaf tissue, and you often see that, and you see tip burn at the distal end or the bottom end of the leaves. Okay. One of the things that happens when we look at the literature is that the sodium generally remains in the roots. Okay. But the chloride, which is quite mobile, goes up with a transpiration stream and ends up in the leaf. But if you have an excess of sodium in the root zone, it may impact on potassium uptake. And why is that? Because this is a monovalent ion, and so is this. And so there is a competitive or an antagonism between the two. And so it may be, if you have a high saline water, saline water, you may want to just make sure that you're getting sufficient potassium into your tree. And then you also have a situation where, because salinity is stressful on the trees, you have an increase in respiration, and the consequence of that is that you may deplete some of your stored carbohydrates. And finally, when you have saline water, it has an effect on carbon assimilation. See? So the activity of your trees are affected when they are subjected to high saline conditions. And we know this. In New Zealand, as an example, we never ever use potassium chloride as a source of fertilizer on our trees. Chloride doesn't exist for us. We only use sulfate of potash, or we use potassium nitrate. See? Because we know that the avocado is quite sensitive to chloride. We know that. And leaf tissue levels are very low. And when you have higher levels, it has an impact, a deleterious impact on the tree and the tree's activities. Water stress. We've used this because it applies to avocados as well as it applies to any other. What happens when you have water stress, like you have now? Most groves have a degree of stress. First, those stomates in the leaves, they tend to shut down. Okay? They are trying to protect the water they have to keep water relations within the leaf. And we also know that the opening and closing of stomates, there is a link with potassium. So you have these guard cells, and these guard cells close or open, and the function of those guard cells is dependent on good levels of potassium. When you have low levels, deficiency of potassium, the guard cells don't work as well as when you have better levels of potassium in your leaves. You have an inhibition of leaf growth. You'll have smaller leaves. True. You'll have an acceleration of leaf senescence. True. We've told you that. You have a reduced number of flowers. Yes. And the point that we made to growers in the last 2 days is that when you have flowering, flowers require much more water. Some of the work in Australia showed that when you have flowering, you put on twice as much water when the trees are flowering. Why is that? The reason for that is that flowers have no transpirational control at all. So everything that moves into the flowers just goes out into the atmosphere. And so you need, during flowering, if you can, you need to have much higher levels of water supply to the trees because there is no transpirational control in flowers. Okay. And so here you also have impaired pollination and fruit set because flowers are extremely sensitive to water deficits, extremely sensitive to water deficits. So you ought to remember that. And then there's also the issue of abortion of young fruits. Okay. We'll maybe talk about that a little bit later when we show you another piece of the presentation. Now, this is some work which was done in Spain and which you might find quite interesting. Flower quality with reference to starch content. First, the stigmas that you have in your flowers, receptive stigmas secrete a complex substance of carbohydrates and lipids to promote pollen germination and growth. Yes. That already tells you that if you have flowers which have low starch versus flowers that have good starch, then we may have a difference in the receptiveness of the stigmas to receive the pollen grain and germinate the pollen grain and take it down the tube. Interesting. Okay. And starch in the flowers also provides a source of energy for tube growth, fully utilized within 18 hours after flowering. Many of your flowers, a pollen grain or more than one comes to the top of the stigma, goes down the style and gets stuck halfway, never gets down to the ovaries, gets stuck halfway, and they simply fall to the ground. And a lot of that occurs. And so they are never pollinated. But even when they get down here and they are fertilized, okay, you need certain preconditions for good fruit set. You need those embryos to grow. You need hormone, principally cytokinin. You need starch to resource it, the little growth of the new seed. You need water, and you need nutrient. And so you have to have all these things prepared for the tree in order to maximize your fruit set. And at flower opening, some flowers show starch amounts 1,000 times higher than others. So not all flowers are the same. Some are well resourced, some are not well resourced. How did they do this? They did it, they took starch. No. They used a dye. I've seen the paper, I have it. They used a dye and then they examined how much starch within the flower, and from that they announced that some of them had so much more starch than others. So we can say this, at flower opening, some have much higher starch levels, and other flowers in your trees have much lower starch levels. The research also showed that early flowers have a higher starch content than later ones. true. The higher the starch content, the greater the ability of that flower to successfully set fruit. And here again, we are saying the same thing, that when you come out of winter, you have to prepare your trees properly in order to maximize their productivity in the spring. And again, if your if your flowers have high starch, we're likely to get better fruit set. And if they have low starch, because we haven't got enough starch to resource them, then we're going to get less fruit set. And finally, the flowers that set fruit have a higher starch content than those that have size. So it doesn't just happen as to be, it often happens because better flowers, better resourced, give you better outcomes. One of the issues that happened in New Zealand in 2010 is we had a autumn flowering, the likes of which we have never seen before. Never. And the consequence of that was that in the spring of 2010, we had the biggest fruit set we've ever had. And we've never had a fruit set like that since, nor have we had a fruit set like that previously. And so autumn flowering is interesting because we also want to try and understand what triggers autumn flowering. Okay. And we also say, as we go in the orchards, that if you have autumn flowers, sometimes if you go in the groves, and I'm sure you've seen this, you have the odd tree that has autumn flowers and maybe a little bit of set, and they're always relatively round. But other times, you may see that it's more widespread. Okay. And so we ask ourselves, what is the trigger? And what does that mean? What does that actually tell us? What is the message if we have a lot of autumn flowering? Okay, so we're going to tell you. In some cases, it's simply because the tree has not performed for 1 year and sometimes even 2 years. And so there's been a buildup of starch in the tree, but we haven't had much crop from those trees. It could be. The consequence of that is that you often get an accumulation of starch reserves. That means the tree is full of starch. It hasn't performed for a couple of years, and so the tree is full of starch, and that's a precursor for autumn flowering. And then, as well as that, you may have favorable autumn conditions in terms of light temperature and moisture, which simply exacerbates it. So we not only have an accumulation, plenty of starch, but now we have a situation in the autumn where we're getting more and more starch being made because we have favorable autumn conditions. And the consequence of that is that we have a leaf buildup of starch. Okay. Now, we've got here magnesium linkage. What does that mean? Okay. If you have leaves that are deficient in magnesium, they have higher starch. If you have leaves in a tree where you have adequate supply of magnesium, they have less starch. Why? Because magnesium, one of the great functions of magnesium is to transport carbon or starch from the leaves down the stems to the roots and into reserves. And when you have deciduous perennials and you have magnesium deficiency, then we always say that the first symptom is not what you can see in the tree, but the first symptom is a breakdown of the feeder root system. And why is that? And that is because you haven't been able to resource the roots because the starch is not flowing down easily because you have magnesium deficiency. So if you have magnesium deficiency, your leaf buildup will be accentuated. Okay? And so then you have what we call impaired feedback mechanism. What that means is there is so much starch in the tree. There is starch in the framework. There is starch in the shoots. There is starch in the roots. There is starch in the reserves. The tree is full of starch and it doesn't know what to do anymore, because those leaves in autumn are still photosynthesizing. There is starch being produced, but we have to find a way to utilize the starch. So what happens is we have what we call leaf-derived floral stimulus involving gibberellin. And the consequence of that is that it bursts into flower at the wrong time of the year. Let me show you. Look, there you have it. The pathways for autumn flowering are carbohydrate pathway, which reflects the metabolic state of the tree. In other words, the tree is full of starch. And the gibberellin pathway for flowering under non-inductive short days, which is autumn. What happens is, instead of this starch working its way and going down here into reserves or any parts of the tree, it can't, because the feedback mechanism is impaired. But it has to be utilized. So what it does is, it goes up to the terminal bud and it breaks out in flowers at the wrong time of the year. That's what it means. So when you get autumn flowering, it's often a good sign, because it's telling you that some of your trees are in good condition in terms of the amount of starch inside the tree. That's what it means. That's how you read trees. You don't simply read it because you have it or you can see it. You read it because you can understand the consequences of what you see. So, what are the messages from the expression of autumn flowering? Well, it's indicative of a good starch status in the tree. True. Anticipates some starch reserve drawdown to resource the autumn flowering, the fruit set, and the fruit growth over winter and spring. So, remember, you're going to lose some of that starch to your autumn flowering and your fruit set and your fruit growth over winter. There's an urgent need. Don't waste that starch. There's an urgent need to maximize or to maximize photosynthetic activity over winter to conserve any decline in starch reserves. Okay? And finally, you may need, depending on the intensity of autumn flowering, you may consider a winter nutrient program with emphasis on nitrogen and magnesium, and, depending on how much fruit you have on the tree, possibly potassium, especially if your trees have set the previous spring and they are heavy in crop. The other expression, and this is what we found. We found that strong flowers, so this is what we'll get in spring if we have intense autumn flowering. Strong flowers well supplied with starch and good fruit set can be expected in the spring. That's what we found. We found that when we had this very high autumn flowering, we had the best fruit set we've ever had. Okay. Be mindful that additional starch will also be needed not only for the flowers and the fruit set, but also for root and shoot growth. True. And so an opportunity exists if you manage your trees well to counter biennial bearing by judicious use of fertilizer and water. You've got your trees in a very good state, metabolic state. So manage them well, and maybe we can carry that over into this next season, and instead of going from a high yield to a low yield, we can flatten it out a little bit. And finally, without prior intervention, trees, if we just ignore it, we just say, well, it's just happening and to bend to that, then trees may be ill prepared for heavy flowering and fruit set and some spring shoot growth and root growth. So the sign is that autumn flowering, you can use autumn flowering to your advantage if you understand what has caused it. Now we'll look at something that we do in New Zealand. And we are cautious, and I'm very mindful that I'm here in California, and conditions in California are very different from those in New Zealand. And that's why we have no Californian growers growing avocados in New Zealand. Because in New Zealand you need a high degree of skill, see, to grow them in New Zealand. See, and so that's why we have no Californian growers growing avocados. And I actually said this in the conference. Ruben was there. I said it in a conference about Australians. It was an Australia-New Zealand conference. And I put up on the screen, they told me, you can't do this. I said, yeah, I can do this. So I put, first thing, skill. See, I put it up there, and then I said, and that's why there are no Australians growing avocados in New Zealand. And Australians, it takes a little while, you know. It took a little while, and then you heard, ooh, in the audience. They didn't catch it initially, then they caught it. And you know, there's a lot of antagonism natural antagonism between Australia and New Zealand. And of course, and Ruben remembers, yeah, well, they would have liked to have lynched me that day, but you know, anyway. We always like to put a little humor into a presentation. So, okay. So why do we do this? Well, we do it because we're trying, and and let me make it quite clear to you that New Zealand is not easy to grow avocado because we are cool, very cool. We are well below the ideal temperatures. So we have to put up windbreaks, and we have to look after the trees, and it's harder to build up our starch reserves. And so for these reasons, we have a slightly different approach to other countries around the world. So we do it because we prolong leaf quality, color, activity, and longevity. And we need to do that because it's tougher in our winter to accumulate starch. And second, we try to do this so that we can increase carbon requirement for fruit growth, flower bud development, root flush, and tree maintenance by holding our leaves, our current leaves, longer into the new season. And it also, we have found that it protects and delays yellowing of leaves due to photoinhibition, oxidation, and nutrient loss. We have found that we can take leaves and they are nice and they're glossy, and then they lose that gloss. And we found that even when we sprayed them with a mixture of magnesium sulfate and low biuretria, we could bring back the shine in the leaves. But we had some problems, and we'll show that to you in the next slide. And finally, it promotes carbon transfer to the roots, which we've shown you. We have difficulty with magnesium in New Zealand because we have very little magnesium naturally in our soils, and we have 50 inches of rain, and so we have a high degree of leaching. So we are very mindful of maintaining high magnesium levels into our leaves. So the case for winter inputs of nitrogen and magnesium, this is New Zealand work. We find that there is a loss of leaf nitrogen over winter of 0.5%, magnesium of 0.05%. We find that soil nutrient levels, even if we finish fertilizing like we used to in May, they were insufficient to provide for adequate supply over winter. That's what we found. We also found that nitrogen and magnesium deficient leaves abscise earlier than normal leaves, and we don't want that. Minimum winter soil temperatures are around 10 degrees, which is similar. Your temperature degree, we've looked at some of your weather data, and some of your weather data showed 10 degrees here in California, which is similar to New Zealand. And finally, we are conscious that high fruit loads may require extra potassium. So, let's look further. What we've done is we have much higher rainfall than you do. Well, at the moment you don't have any rainfall because the gods are against you. See? You can't buy rain. And with depreciating dollars, you'll never be able to buy rain. See? Okay. Yep. Next. The monthly winter foliar applications, that's what we used to do. We used to apply it once a month. And it was insufficient to arrest leaf decline. So now we apply fertilizer 12 months of the year. And over winter, we are putting on roughly 100 grams of nitrogen in a tree for a crop load of around 10 tons. So that's 2,200 pounds a ton. So that's 22,000 a hectare. That's what, 8,000 or 9,000 pounds an acre there, see? And we've noticed a positive response as a consequence of doing this. So for us, we also know that high nitrogen in our leaves protects them against cold injury, which is a serious concern for us. And finally, we apply the nitrogen either as potassium nitrate. We want a nitrate component rather than an ammonium component because the conversion of ammonia to nitrate is much slower under conditions of low soil temperatures. So here we use ammonium nitrate here, NH4NO3, or we use potassium nitrate over here. So that's the approach that we take in order not only to keep our leaves green, to maximize carbon assimilation over winter, but also to get longer lifespan out of our leaves. This is some work that was done by Jonathan and I, looking at the relationship between the roots and the top, above portion of the tree and below portion. See? So first of all, we took the 9-year-old tree and we cut it down the side like this, took everything off, and we pictured it. We also brought in soil scientists, and we dug trenches from here all the way out, because in the old days they used to say, oh, no, you just put the fertilizer around the drip line. We found that not to be the case. We found that there was high subdivision of roots in the upper parts of the soil, all the way from the trunk all the way out to the drip line. And then, having done this, we cut the tree off over here. We got this huge digger and we dug the tree out. And then one of my roles was to wash the tree so we could show you what the tree looked like. This is almost certainly a Zutana rootstock, and that's Hass. Okay. And so we said the above ground portion of trees does not necessarily reflect the size and root system. So what did we take from this? Well, we know that when it comes to carbon apportionment, it's always existing fruit, seed and fresh, then it's leaves, then it's shoots, then it's branches and framework, then only its roots, and finally it is into reserves. So it's last in carbon apportionment hierarchy before the reserves. Okay. That's the first thing. Secondly, it's generally accepted that root systems represent no more than about 20% of a tree on weight basis. Okay. But roots are very important because it's the site for cytokinin and abscisic acid. That's the bad one, but it's also the site for the good one, cytokinin. Okay. And while transport of auxin to roots triggers flush, you need, it's true, so auxin moves from terminal buds, for instance, and goes down into the root system, and it triggers a flush, and that flush produces new root apices, little root tips, and that's the site where we get a production of cytokinin, and then the cytokinin moves back up to the tree. But we can only really get a trigger flush if we have starch to promote the flush. So if trees are starved with flush, well, then they're not. If roots are starved of starch, then we're not going to get the flush when we should. Okay. So that's what happens. And it's called dominance. And the degree to which you get spring shoot growth depends on how much auxin has moved from the terminal buds down into the root systems and produced cytokinin to produce an expression of shoot growth in the spring. And here you see something that was done by the Californian Avocado Commission. I'm not going to dwell on it, but here you have heavy fruit flowering, heavy fruit set, not a great deal of shoot growth, and only a small amount of root flush. But when you reverse it and you have low flowering, low fruit set, then you have much greater activity in vegetatively and much more root activity over here. And what you're trying to do is to balance that out. You don't want extremes from high crop loads to low crop loads to high crop loads. What you're trying to do is balance it out. And one of the ways you can best balance it out is to maximize starch, because what it's saying is the starch was taken up here, it was taken up here, and as a consequence of that, you only got a degree of shoot growth. And the next year, we didn't take up much starch here, and the starch wasn't utilized here. So now we have plenty of starch, and so now we have the shoot growth and we have more root growth. And what you want to do is try and find a balancing effect. So, as we conclude, reading your trees points to remember, first of all, the quantity of nutrient loss through leaf and flower abscission is substantial, true. Some of this work was done by a man called Cameron. It was done here in California. It's old. It's nearly as old as I am, right? He was 1950 something, and I was born. Well, that's none of your business. I mean, ladies don't tell me when they're born, so why should I? Anyway, Each year, a tree loses 40% of its nitrogen, 60% of its P and K, 75% of its magnesium, is what Cameron found when he did this work. The trees were relatively large. Another thing we found is that flowers are high in nitrogen, up to 3% dry matter. We found that there's some recent work by Carol Lovett, and she went out and did work in a number of counties, and that work showed about 2.7, 2.8%. So our data and the data here in California are not too far apart from each other. But what that means is serious, because if you have a big tree, now we're not talking about trees that are fruit, but the big trees, and they are full of flowers, then what Cameron found was that dry weight of flowers could vary between 2 and 10 kilograms depending on tree size. That's dry weight. So let's say you have 6 kilograms of flowers and you have 3%. Then it means the flowers took 180 grams of nitrogen. That's 180 grams. That doesn't mean that if you put 180 grams on the ground, all 180 grams go into the tree. I mean, there's an efficiency. Maybe 70% of what you put on the ground actually ends up in the tree. But you should be mindful that when you have heavy flowering, it is demanding on nitrogen, because your nitrogen content of flowers is high. California, about 2.7, 2.8%. And finally here we say that apple-sized leaves contain 0.8 to 1% dry matter of nitrogen. In other words, they're literally buggered. They don't function at this sort of levels. So they're ready to fall off. And trees know that. Why do trees know that? You have two types of leaves. You have a leaf that contributes to the tree, and you have a leaf that doesn't. That's actually a cost to the tree. Trees know this. So when leaves are, for a long period of time, costing the tree, they're taking carbon away from the tree just to sit on the tree, then the tree sheds them. So you'll always find that if you can't resource the leaves, the tree itself takes steps to remove those leaves because they are costing the tree. They are not contributing to the tree. More points to remember. Carbon resource limitations are linked to poor fruit sets. Yep, true. Flowering is expensive in terms of carbon, in terms of nutrients, in terms of water. Please remember that. Remember that. It's important. Don't stress flowers. You won't get good sets. Current assimilation over overwintered leaves reduces the depletion of starch reserves during spring. You've got two choices. You take it out of starch reserves, or you can make those overwintered leaves function and compensate for any losses taken from reserves. And finally, we say in a simple sense, leaves are the factory, roots are the control room. Roots, not all hormones are produced in the roots, but two crucial hormones, abscisic acid and cytokinins, are. So, our final slide, I think, or second final slide, healthy overwintered leaves, well supplied, nitrogen, chlorophyll, starch, are retained longer in the new season, provide stored and current photosynthetes for flowering, fruit set, spring vegetative growth, and for the late hanging of fruit, which occurs here in California. And constructive husbandry with sufficient light. We see a lot of orchards that are hopelessly too closed. The whole bottom of the tree doesn't almost exist. All I see is some branches. Everything is on a single plane, horizontal plane at the top of the tree. That's not smart farming for light. So, constructive husbandry with sufficient light enhances the probability toward a more regular cropping outcome. See? And next, leaf size, color, longevity are indicators of tree health. True. I mean, you see a lot of orchards, the leaves are small. That's not a good sign. You know how big a leaf can grow, probably 9, 10 inches. And that's how your leaf should look. So leaf size is a very good indicator, color and also longevity. Another thing we do is in New Zealand is we go to each of the two quadrants, north and south. We usually go, in our case, to the south, in your case to the north. We pick a good leaf on that side and we take it around and we put it next to a similar leaf on the other side. So in your case, you take it from the north, bring it to the south and compare them. If the south leaf is not looking as good as the north leaf, then you can expect that deterioration to continue unless you do something to arrest the decline. So a very good test is simply to go to your north face, pick a leaf there, because they are usually generally darker green because they have less function on that side, bring it around and compare it to a leaf on the south face. Another way to look at health of trees is density of canopy. We always say that you should not be able to see any of the branches, the framework branches of a tree. They should be covered by foliage. That way you can make sure that you're maximizing the interception of light and the production of carbon and carbohydrates. And finally, when you have deficiencies in tree health, you encourage root rot infection, because root rot infection, there is a process called chemotaxis. Chemotaxis means that when trees are unhealthy, the roots release an exudate and the zoospores are attracted to the exudate and attack the roots. And that process is called chemotaxis. And so, as I come to the end of the presentation, my thanks to Index Fresh, to John Cornell, and finally to Dr. Jonathan Dixon, and thank you very much.
You account for, during the winter and in spring, an infestation of Perseamites.
I can't answer that.
Okay.
We don't have that. But it's not my field.
Lucky you.
Well, it's that, but it's also, pests and diseases are not really my field. I don't do it. We reckon that there's so many chemical reps out there, they can do it. I don't do it.
I guess what I was thinking,
Yep.
there was considerable damage done to my leaves, so I was wondering if there were ways of compensating for that nutritionally or culturally during the winter, so there'll be less drop in spring and they'll have some function in spring?
It's what actually attracts the infection in the first instance. I can't answer that because I don't know that. But the best remedy you have is that you attack the infestation as early as possible so that the degree of leaf damage as a consequence is minimized.
Is it possible to over-apply nitrogen? I was told that if you put too much nitrogen in, you have the leaf growth, but the lack of fruit growth.
It's a good question. Thank you. It's a good question. There was a time in New Zealand where we weren't getting much fruit set. And some of the consultants said, well, the reason is because there's too much nitrogen in the spring. The program used to be that we used to apply nitrogen or all fertilizers until May, and then we applied no further fertilizer until late August or early September. Okay. And so when you came to September and you put on your fertilizer, the tree wasn't sure exactly what you were trying to ask the tree to do. Were you asking it to flower or were you asking it to produce shoot growth? And the latter is likely because avocado has a vegetative bias. But what we found is that if you apply small amounts of nitrogen all year long, then it doesn't have that trigger effect where it simply directs the nitrogen simply into shoot growth in the spring. So we're not getting that. What we do now is, if you condition the tree to small amounts of nitrogen right through the year, you get a different response than when you allow the leaves or the tree to get deficient in nitrogen over winter, and then all of a sudden you apply it in the spring. So what we have now found is that we don't get that. We don't get a acceleration or a burst of leaf growth in the spring if we simply apply nitrogen all through the season. But to be fair to you, we have very high rainfall in winter. So although you saw the number there of 100 grams, we have something like 6 or 7 inches of rain during those months. Okay? So the efficiency, in other words, if I put on 100 grams, how much of the 100 grams did we actually get in the tree? Good question. And we'll only get into the tree what the tree needs. Trees don't store nitrogen. If I put on twice as much, I don't get twice as much in the tree. I only get into the tree what the tree requires. And that applies to everything you do whenever you do it. There's no purpose to over-fertilize a tree, because a tree will only utilize what it needs because its growth rate or its activity is related. The activity is related to absorption of nutrient. So if you put on 3 times as much, you don't get a leaf content of much higher than if you put on the normal amount, because that's what happens. So we have found that that's enough to maintain the nitrogen in the tree without allowing levels to drop. And then in the spring, we simply carry on. And we do not have that reaction that you raised. It is more likely to get that reaction when you allow leaves to fall in terms of content, and then suddenly you apply a large amount later.
Dr. Dixon said that New Zealand, some of the growers are using a complete fertilizer that is not just a single elemental fertilizer, that it has your minors, it has your magnesium sulfate. When you showed the photograph of the shoot to the root ratio, we didn't see root hairs like we have here. Now you have a different...
we washed it off. No, we just... No, you couldn't. You couldn't. When you pull it out and tear it all off, that wasn't it. But I'll take your question.
So my question is that you didn't think that the root ratio to shoot ratio was a 1-to-1 ratio of dry weight matter.
No.
That there was more shoot.
No. It's a good question. We'll start with the first bit. The all-encompassing fertilizer that you talked about was put together by Jonathan Cutting and myself. It's a field that I'm very familiar with, the fertilizer.
So it's like a Hoagland.
It has all the nutrients, all the trace elements, and then because of our conditions, it has added magnesium in the form of kieserite, which is a magnesium sulfate. And it has added boron, and it has added zinc. It's very successful. And it is better than simply buying something that's not adapted or not suited directly to avocado. That's the first point. The second point is that we have grown our trees using Zutana as a rootstock, and we did that because we were told that Zutana was more cold hardy. The problem with that is that we have overgrowth. In other words, when we look at our trees, the rootstock is here, but the scion is thicker over here, and there's a degree of incompatibility. And the consequence of that is that after around 20 or 25 years, these trees run out of puff, okay? Because we allow unfettered growth above the ground, and the consequence of that is that carbon allocation always goes to those parts first and goes to the roots last, and that allocation means the roots remain relatively constant while the rest of the tree grows and grows and grows. Okay. But what we are now finding that if we have pruning intervention in our trees, so that we manage the trees to a height of 12 or 14 feet, and every year we do a degree, then we change the shoot-root balance as a consequence. Okay? So we're not allowing the top, the above portion of the tree to grow larger than a certain size. Okay? And that allows us to bring light into the orchard at a certain population of trees. Okay? The consequence of that, in turn, is that the apportionment of some of the carbon to the roots is more likely than if we allowed unfettered growth above the ground. And the consequence of that, in turn, is that that overgrowth tends to disappear. See?
And you talked about the drip zone, and you talked about the actual feeder roots that are going out there. What are the feeder roots going beyond the normal canopy? Even though, let's say, you pruned, Was it still extending beyond?
It tends to, what we found is, of course, the litter is underneath the tree.
Right.
They like the litter. Your your orchards are bare ground. Our orchards are grass. Grass, of course, is competition. So the grass, the sward, is competition. We found that after we got out of the drip zone, out of the drip line a little bit further, we found that root density or root intensity diminished. So, but what was surprising for us was the degree of subdivision under the tree in the littered part, which is understandable. Those conditions can be very favorable. There are one disadvantage. What we did is we went into large trees, we put buckets underneath the tree canopy and buckets just on the outside of the drip line. And what we found is that after rainfall, we found that there was more water collected in the buckets on the drips, on the outside on the drip line, than there was inside. Well, that's just a consequence. Some of it runs off the leaves and runs out. And you'll find that even in forests, you'll find the same consequence. And some of the water actually stays on the leaves, and doesn't find its way to the bottom. But what we have found is healthy subdivision of roots all the way out to the drip line. So now we are telling growers they have to fertilize right through to the trunk and not just on the outside.
I'm following potassium nitrate.
Yeah.
Put it on,
Yeah.
goes up in the trees, gets into the leaves fall off and get back to the ground. What happens to the nitrate, potassium nitrate? Do I concentrate it by adding it to the soil?
Nitrate is an anion. Potassium is a
What
cation.
about the anion? Where does the nitrate go?
No. The nitrate is used, there are processes within the tree, whether it's protein synthesis or whatever, the growth processes of the tree. The nitrate supplies the necessary amino acids and everything else to produce the expressions that you see. But the reason why we like potassium nitrate is because when you have a cation, you need a corresponding anion in order to facilitate uptake in the trees. Okay. There are three principal anions. The first is nitrate, the second is chlorides, and the third is sulfate. The way sulfate goes into a tree is complicated. I won't go there today. It's complicated. But the other two are highly mobile, and so they are favorable. So what we're saying is when you have the potassium, you need a carrier to take the potassium up into the tree. That's what happens. As we showed you here, some of the litter, some of when the leaves fall, contain a degree of nitrogen and other elements. And there is mineralization, and there's a breakdown of the material, and it goes back into the soil, and some of that mineralized N will re-emerge into the tree. And we see this. Let me give you an example. A good example of mineralization is grassland. So we have grassland for a long period of time. We have high organic matter, everything else. And then we plow it over and we grow a vegetable crop, for instance. Well, in that case, we can use less nitrogen because there's a contribution of mineralized N. Whereas if we were fallow and we were continuously cropping, then the amount that can be contributed from the soil to the next crop is much lower.
So you're saying that there is nitrate from one crop to the next one in an avocado tree?
I don't know whether that's ever been measured, and I doubt that it has.
Put a ton of nitrate on an acre.
Well, if you put a ton of nitrate on, I'm going to smack you because you put too much on.
But how much do I lose the next year?
If you want,
You're organic, you don't fertilize.
easy? Hey, well, what about that?
How's a friend there?
Shall we show him the door now, or only at the? Oh, have you eaten breakfast?
Yes.
Oh yeah.
I got the good cookies too.
All right. Huh?
What are the consequences
Of what?
of girdling?
We don't. We see that you do. The idea of girdling is to maintain the carbohydrate that is produced in that part of the branch, and hopefully that by trapping the the current photosynthase or the carbon in that part of the tree, you will get the expressions that you want, and that will give you an increase in crop. Now, we don't do it.
Why?
We have tried it, but we found that we couldn't quite work out the timing for it. So sometimes it was erratic. Sometimes you may got a little bit of it, sometimes you don't. We do a lot of it in kiwi fruit, a lot of it, but we don't do a lot of it in avocado. But it is not a silly suggestion that perhaps we should look more closely at that practice in New Zealand.
Because before you cut
Yeah.
the branch out,
Yeah.
can't you get a good crop off it, girdle it, and
Well, maybe. I can't give you whether there's a contribution to it or not because we don't do it. Ruben.
First of all, with regarding to girdling,
Yeah.
you already have about 80% of your flowering determinate.
Correct.
And they're already causing you a problem, and now you're suddenly going to girdle, which is going to give you almost 100%
Yep.
of your flowers,
Yep.
which, at least in this environment, is really bad because there's no leaf cover, and that's what you're trying to grow is leaf, not necessarily.
So are you opposed to the concept?
Well, if you girdle and remove all the determinate ones and leave only the indeterminate, then you're going to get the benefit. But not girdling is the wrong word. It's cincturing, if anything.
Yeah.
You know, and you will get that difference. But it's
Now, do you understand what he's saying? He's saying that you get determinate panicles. So in other words, you don't get a shoot coming. Okay, all of that carbon is taken up in the flowering. Now, the difficulty with that is that you need shoot growth in the spring in order to provide carbohydrate. And what Ruben is saying is you run that risk because you don't have it. Accompanying to the flowers and the fruit set, you need current photosynthase from spring shoot growth. And you are compensating that by girdling or cincturing those branches. Do you follow that? Yes. Okay.
my other comment was regarding the nitrate
Yeah.
comment.
Well, he's organic, so
I don't really care.
he's half crazy.
Well, he can
he's
use-
half crazy before we get. Can
Organ-
you really reason with him, Ruben?
No, yes, because some organic.
So you're right or wrong, and I'm right.
Okay.
Well, now you.
20% of organic fertilization could come from sodium nitrate, which is the nitrate. So, at least in California.
They allow that?
Yeah.
Oh, let's see.
Okay. No,
Well, you know, this is America. Well,
Yeah.
Well,
But with regard to nitrate,
Yeah.
nitrate can function easily in cold soil temperature.
Correct.
Much better than anyone that needs conversion by either an enzyme or
correct.
bacteria.
Now you listen to this. What he's saying here is that unlike ammonia, which has to be converted first to nitrite and then to nitrate through the process, okay? What happens with nitrate is that it doesn't. So any winter production, okay, where you have cool temperatures, you use nitrogen in the form of nitrate, not in the form of ammonia.
Yes.
But you don't use either because you're organic.
In a very old grove, after you put on nitrates for years and years and years and re-put it into the soil, and if you start with a young tree in DG with nothing in it, you need to fertilize.
Well,
You keep fertilizing it out, and you continue to put it on, and it goes into the soil, and it's like grass. You turn it over, you've got something to grow on. Is it possible to always get the soil ready so that you don't have to fertilize it?
but I don't quite understand why, if you're organic, that you can apply fertilizer to it.
I didn't apply it, I'm saying I don't.
Are you cheating on your certification? Is he? I've got. Look, I think you're right, Ruben. We got to worry here. You've got to send the commission out to check on this guy. What is this?
Well, I just one last
Yep.
comment. You made a statement that's totally contradictory to what the common advice
Yep.
that both Jonathan Dixon and Carol Lovett has
Yep.
is to apply in a phenological points extra nitrogen. You're saying don't do that, just do it straight, which I agree with you 100%. But obviously, some people are practicing this kind of
That approach, the only trouble with that approach is that we go back to him. So they say, well, you know, phenologically over winter, it's quiescent, there's not much going on, so we don't do anything. Then we apply it in the spring, and there's a risk that we end up with a surplus of spring shoot growth. That was why I understand that, because there are a lot of crops. We'll just take that point further. There was some wonderful work done in Australia where they decided to understand the phenology of the tree. In other words, the whole cycling of a tree before they created programs to maximize the productivity of the tree. It's some wonderful work. It goes in macadamia, it goes in lychee, it goes in mango, it goes in all sorts of things. Because subtropical trees or evergreen trees are far more complex than deciduous perennials. That's why. So we've got to be a little smarter. Yep.
When you're reading a avocado tree, depending if it's in Australia or in New Zealand or somewhere in California, you can see when you see magnesium presence or deficiency. You can see when a tree's been fed with a lot of Epsom salts.
Some trees.
But when I see a rose, I can say that I've seen it's been fed with magnesium sulfate. It's obvious.
Yes.
Same thing I can see when I feed my trees Epsom salts. Do you think that we're not feeding with magnesium sulfate enough?
Some trees exhibit magnesium deficiency early. One of those is citrus. You get the inverted V in it. Okay. The question of whether you're supplying enough or not, in New Zealand we have a level in our leaf test of 0.4 to 0.7. We struggle to reach 0.4. Struggle. Okay. There are other parts of the world where 0.5, 0.55 to 0.7 is easily attainable. You've got to be careful comparing California to New Zealand, because as I explained earlier, New Zealand's issue is that we have very high rainfall and we have soils that are deficient in magnesium. There was one other thing that I didn't touch on that I would like to touch on, and that is growers, what they do is they staghorn their trees. So the tree is a living organism functioning in every way, and then over a matter of a couple of hours in a chainsaw, it has no leaves, it just has a framework. We don't believe in this. We're not saying that you're right and we're not saying that you're wrong, but we are totally opposed to this. And the reason for that is twofold. The first is we believe that you get a dieback of the roots because you can't resource the roots now because you've removed the canopy. The second is that we believe that when you do that, to bring the tree back into a balance between reproductive and vegetative, it takes longer. What we do is we will prune the tree, but we will leave at least one limb or maybe two limbs so that the tree continues to function normally while a degree of pruning or staghorning takes place on the remainder of the tree. And we also find that when we do that, trees come back into bearing sooner than when we staghorn the trees.
You talked about the difference in leaf thickness between north and south. Is that normal, and what does it tell you?
It tells you the function. Thicker leaves are functioning more. Thinner leaves function less. Go and do that. You go further in the tree, they'll be even thinner. Yep.
When should I do the pruning? When's the most effective? At the end, after the last flush of the summer?
In New Zealand, we would prefer to prune to capture the spring shoot flush. The problem with that is that in many cases we can't get the fruit off before we do that. But what we want to do is get as much flush from our trees as a consequence of pruning in the first year. So we want to do it early. But we can't always do it early because there is fruit on the tree.
On the other hand, if you let the that flush sort of mature, and
which flush?
The first flush, the spring flush. Then you get a lot of production of starch, that goes down to the roots, then you take that 2 feet off.
Well, we don't actually do it like that. But our problem is that the summer flush is truncated. It can actually, sometimes it doesn't actually complete itself because we are so cool. We are completely different. We're not concerned about the question of sufficient carbon because we never completely prune the tree totally. Okay. We don't like to prune it at a high level, just simply cut it, because then all it does is it reaches up for the light again. In terms of pruning in a general sense, probably New Zealand is behind California because you have much older trees and an older industry and many more trees in the ground and many more opportunities to experiment than we are. But we are starting now, and we realize, and I think the Californian industry does too, that pruning we need to start much earlier in the life cycle of the tree rather than waiting for the tree to get to a stage and then try and correct it.
I'd like to make a comment regarding this
That's not a question.
winter. No. It's a question. Winter application of this potassium and all this other stuff. You actually talking about putting it foliarly?
No. The new fertilizer programs, which were done with Jonathan Dixon, Jonathan Cutting, and myself, we prepared them. We put it on the ground, which includes potassium. Of course, the heavier the crop, the more potassium we need over winter, and the lighter the crop, the less we need, which is fair. We've never applied potassium as a foliar. We don't like foliars generally because there's a wax layer on the cuticle of the leaves. Okay. We use low biuret because the biuret is deleterious. It's phytotoxic. So we use low biuret urea at 1%. We use magnesium sulfate or Epsom salts at 0.5%. But we have moved away from that. But we never applied, like, say, potassium nitrate as a foliar, never.
Well, you used to, at least.
Well, they might have.
Cuttings, but
there's a lot of crazies in New Zealand. I mean, there's actually more in America because you guys have got guns with your crazies, and we don't. You know, we've just got our two hands.
Yeah. So you must have a very high level of cation exchange or a lot of organic matter. So you can put this material in there. It's actually held in the soil rather get washed away because a lot of those things are very soluble.
The point that Ruben makes has some validity because the difficulty is that when you have very high rainfall and you have soluble fertilizers, then you have a degree of loss. Okay? And that is agreed. But at the same time, we have an understanding of that we need to keep the condition of the trees as close to the time in which we took the leaf analysis. Those 5 months over winter, we like the same green leaves, if we can, that we took when we took our leaf samples, to be present in the tree at the end of winter. But if you are saying to me, what is the recovery of fertilizer in winter? It is much lower than it is during periods of lower rainfall. Correct. Yep. Now, is that it? 1 hour, 50 minutes. That's it.